First, here is the first example about construction of shear moment diagrams for beams. For the beam loaded as shown below, construct the shear and moment diagrams, also sketch the elastic curve. So let's apply now the reactions. Reaction at C horizontal is 0. Then let's sum up moment about C equals 0 clockwise as positive. But before that, let's divide this trapezoidal loading into rectangular loading and triangular loading so that we will have easier calculation for the moment arms. So summation moment about C equals 0 clockwise positive. So we have RB times 10 minus 20 times 12.4 minus 0.5 of 2.4 times 48 times 10.8. 10.8 is 10 plus 1/3 of 2.4, so 0.8, so 10.8. Then my plus, or RB times 10 equals 20 times 12.4 plus 0.5 times 2.4 times 48 times 10.8 plus 12 plus 11.5 times 24 times 5.75 from this, so 5.75 minus 1.5 is 4.25, then plus 1/2 of 0.5 or 0.5 of 11.5 times 24. This is supposedly 2/3 of 11.5 or 23 over 3. 23 over 3 minus 1.5 moment arm of this triangular load is 37 over 6. So solving for R sub B is 289.408 kilonewtons upward. Likewise, summation moment about B equals 0. So we have R sub C times 10 plus 20 times 2.4 plus 1/2 or 0.5 of 2.4 times 48 times 0.8, then equals 24 times 11.5 times 5.75, then plus 0.5 of 11.5 times 24 times 23 over 6, or 1/3 of 11.5 is 23 over 6. So solving for R sub C is 202.192 kilonewtons. So before proceeding to the shear diagram construction, you have to sum up forces Y if it is equal to 0. So I already checked it, then it's up to you to check also summation versus Y. It must be 0 so that to make sure that the shear and moment diagram would be correct. So let's call this intensity of loading W sub C. Then from this triangle here, by similar triangles, W sub C minus 24 as to 1.5 equals 24 as to 11.5. W sub C minus 24 as to 1.5 equals 24 as to 11.5. So W sub C is 624 over 23 kilonewton per meter. Then call that area 1, the triangle, then area 2, this trapezoid, area 3, this another trapezoid. Area 1 is negative 0.5 of 2.4 times 48 is equal to negative 57.6. Area 2 is negative 0.5 of quantity 48 plus 624 over 23 times 10, so negative 375.65. Then area 3 is negative 0.5 of WC quantity 624 over 23 plus 24 times 1.5. So area 3 is negative 38.35. Then let's call this intensity of the load W at distance x sub 1 from D. So its distance from D is 11.5 minus x sub 1. So the shear diagram, we have to go down 20. So from 0 to, we have negative 20. Then plus area 1, which is negative 57.6. This is 0 to negative 48 ordinate. So it is negative increasing. So negative increasing slope like that. From 0 slope, because 0 intensity of load, to negative 48 slope. So negative increasing, negative 20 plus negative 57.6 is negative 77.6. Then plus R sub B, which is 289.408. So negative 77.6 plus 289.408, we have 211.808. 211.808 plus area 2, which is negative decreasing. So negative decreasing slope looks like that. So negative decreasing ordinate, negative decreasing slope. So 211.808 minus 375.65 is negative 163.842. Then negative 163.842 plus r sub c, which is 202.192. So it is 38.35. And 38.35 plus negative 38.35, it's 0. We have negative decreasing slope or negative decreasing ordinate, so negative decreasing slope like this shape here. So that completes the shear diagram construction. Then let's proceed to the moment diagram construction. We will call this area 4, this one area 5 at distance x sub 1 where shear is 0, then area 6, then that one is area 7. So shear in BC is 211.808 minus the area of this spandrel, area of this trapezoid, which is 1/2 or 0.5 of quantity 48 plus W, and W is to be derived or solved later, then times distance between them is x sub 1. So by similar triangles again, from this triangle here, so this height of the triangle is W minus 24. W minus 24 as to 11.5 minus x1 equals 24 as to 11.5. So W is equal to 24 plus 48 over 23, 11.5 minus x sub 1. Substitute in formula shear BC, then equate to 0 because we want to get 0 shear. As the shear here is 0, so that's why we want to solve for x sub 1. So simplifying, we have 211.808, 48 plus 24 plus 48 times 11.5 over 23 is another 24, so 96. 96 times negative 0.5, negative 48 times x1, so negative 48 x sub 1. Then 48 over 23 times negative x sub 1 times negative 0.5 is positive 24 over 23 x sub 1 times x sub 1, so 24 over 23 x sub 1 square. So shear BC is 211.808 minus 48 x sub 1 plus 24 over 23 x sub 1 square, then we equate to 0 to get x sub 1. So solving for x sub 1, it is 4.944 meters using quadratic formula. Having found x sub 1, 4.944, so we can compute the intensity of the load where shear is 0, which is actually interpreted as the slope of the tangent at shear is 0. So 24 plus 48 48 over 23 times 11.5 minus 4.944, W is 37.682 kilonewton meter downward or negative slope. So that slope will intersect this vertical here and this vertical here. So let's draw the tangent first. To compute the ordinates of the vertical here, it is simply slope times x sub 1. So 37.682 times x sub 1, 4.944. So we get 186.3. Likewise, slope 37.682 times this distance is 10 minus x sub 1. 10 minus 4.944 is 5.056. So that's why it is negative 190.52. Again, 37.682, this is supposedly negative, times this distance is 10 minus 4.944 or 5.056 is negative 190.52. So to construct the moment diagram, here it is. So first, 0. So by the way, area 4 is area of rectangle plus area of spandrel. Since area 4 is negative, I precede a negative sign here and compute the area as positive. So 2.4 base times height 20. Then for the spandrel, because the tangent is here is horizontal, so this is automatic as spandrel. So 1/3 of 2.4 times 57.6. The height is 57.6. 77.6 minus 20 is 57.6. So that's why area 4 is negative 94.08. So from 0 moment here, this is negative increasing ordinate. So the curvature is the same as that, negative increasing. And the ordinate here is negative 94.08. Then from negative 94.08 to this point where the tangent is horizontal, we have positive decreasing ordinate, so positive decreasing slope. So it looks like that, the curvature looks like that. Then the horizontal tangent at 0 shear. Then area 5 is equal to area of triangle plus area of spandrel. Area of triangle is 0.5 of x1, 4.944 times 186.3 plus spandrel 1/3 of 4.944 times quantity 211.808 minus 186.3. That's the height of the spandrel. It is 25.508. So the area is 502.57. So negative 94.08, positive decreasing, plus 502.58. So we'll get the ordinate there is 408.49. That's the maximum moment also. Maximum positive moment is 408.49. Then plus area 6, we have 0 to negative 163. So negative increasing ordinate. So negative increasing slope here in the moment diagram. So it looks like that. So area 6 is negative. So negative area 6 is area of triangle minus area of spandrel. So triangle 0.5 of 5.056 times 190.52. That's the area of the triangle. Then minus the spandrel 1/3 of 5.056 times this height is 190.52 minus 160.842 is 26.678. So area sub 6 is equal to negative 46.673 kilonewton meter. So therefore, the ordinate here is 408.49 plus negative 46.673 is negative increasing, so negative 28.183. Then to solve for area 7, let's draw the tangent. The tangent is negative 24 because we have intensity of 24 downward. Negative 24 times 1.5 is 36, the ordinate there. So this area 7 is area of triangle plus area of spandrel. Then area 7 is 0.5 of 1.5 times 36 plus 1/3 of 1.5 times 2.35, where 2.35 is 38.35 minus 36. So its area is 28.175, or if rounded off to 2 decimal places, 28.18. This is negative 28.18 if rounded up to 2 decimal places, plus 28.18, so that makes it 0. But there is a very small discrepancy here, so we just make it 0. And it is positive decreasing, so positive decreasing slope would be like that, just like this. So 0. That's the moment diagram by parts. And then we draw the elastic curve. We have 2 points of inflection, 0 moments. Then from the left end to this 0 moment here, the moment is negative, so we have concave down elastic curve. Then between these 2 points, positive moment, so concave up, positive moment is concave up curvature through C, then through this point of inflection. Then between these 2 points, we have negative moment, so concave down elastic curve. So this is the elastic curve, concave down, concave up, then concave down. So that's the shape of the elastic curve. The elastic curve is above A and above D because the moment at the center, the load at the center is very heavy, that its moment is very high compared to this moments here. So the tendency is this will bend great in the center, that even if there are loads at the overhang, then the elastic curve will still lie above that overhang, above the horizontal. So that's it. And let's proceed to the next problem. So next problem is about construction of shear moment diagrams for girders. For the girder loaded as shown below, construct the shear and moment diagrams. Also sketch the elastic curve. So we have here the girder. The girder is weighing 2 kilonewton per meter as shown in the figure. So first, let's compute the reactions at these floors here. Then let's transmit these reaction forces to the girder so that we can analyze the girder. So this reaction is 583/7. To get that, you sum up moment about this point here, panel point. So reaction times 3.5 equals 12 times 5.5 times 2.75 plus 20 times 5.5. So again, 12 times 5.5, 12 times 5.5 times moment arm 5.5 over 2, or times 5.5 over 2, then plus 20 times 5.5, then divided by the distance between this reaction here and this point here is 3.5. So divided by 3.5, it will give us 583 over 7. Likewise, if you want to compute the reaction just to the left of this point, we sum up moment about this point here. So reaction times 3.5 plus 20 times 2, then minus 12 times 5.5 times 0.75, because 2.75 minus 2 is 0.75. So 12 times 5.5 times 0.75 minus 20 times 2 divided by 3.5. So the reaction just to the left is 19 over 7. Then reaction just to the right, so let's consider this beam here, because the loading is at the center and the concentrated load is also at the center. The reaction just to the right of this support or this floor beam here is equal to 1/2 of 12.5 times 6 plus 1/2 of 30. So 12 times 6 divided by 2 plus 30 divided by 2 is 51. So just to the right, we have 51 kilonewtons. Just to the left is also 51 kilonewtons upward. And finally, in this portion of the floor here, we just to the right reaction times 4, then equals 15 times 6 times 1. So 15 times 6 times 1 divided by 4 is 22.5. So just to the right is 22.5 upward. And just to the left, we sum up moment about this point here. Reaction times 4 equals 15 times 6 times 3. So 15 times 6 times 3, then divided by 4 is equal to 67.5 upward. So that's it. Then we draw another diagram. Let's just concentrate on the girder, and we transmit these red reactions. So first at this end here, 583 over 7 downward. Then we have 19 over 7 plus 51 equals 376.7 downward. Then here we have 51 plus 22.5 is 73.5 downward. And lastly, we have 67.5 downward. So this is now the girder, and we can now analyze this. We first solve for the reactions at A and at B. So reactions at A and at B. Summation moment about B equals 0. Clockwise positive, so we have RA times 9 plus 67.5 times 2, then equals the weight of the beam, 2 times 15.5, 13.5. So this is 4, 10, 11, 13.5. So 2 times 13.5. Then the moment arm is 13.5 over 2, 6.75. 6.75 minus 2 is 4.75. Then plus 73.5 times 2. Then plus 376 over 7 times 8. Then plus 583 over 7 times 11.5. So distance of 583 over 7 from B is 11.5. Solving for R sub A is 169.75 kilonewtons. Likewise, summation moment about A equals 0. Summation moment about A equals 0, counterclockwise positive. So R sub B times 9 plus 583 over 7 times 2.5 equals 2 times 13.5 times 4.25. 4.25 is 6.75 minus 2.5. 6.75 minus 2.5 is 4.25. Then minus 376 over 7 times 1 minus 70 or equals, no? Equals 2 times 13.5 times 4.25 plus 376 over 7 times 1 plus 73.5 times 7 and plus 67.5 times 11. Solving for R sub B is 135.25 kilonewtons. Then, as I said, perform the customary check, summation versus Y. I leave that to you because I already checked it. Then it should be equal to 0 before we construct the shear and moment diagram, which will be presented on the next slides. Continuation of the construction of the shear moment diagrams for the girder. Remember that we already solved RA and RB. So first, we go down. 583 over 7 in decimal is equal to 83.286 kilonewton. So go downward. Minus 2 times 2.5. So negative 83.286 minus 2 times 2.5, the weight of the girder. So we have straight line, negative 88.286, constant negative. Constant ordinate negative. So that's why constant negative slope. Negative 88.286. Then add the reaction at A, which was computed in the preceding slides. So you'll get 81.464 after negative 88.286 plus the reaction computed earlier is, so we get 81.464. Then minus 2 times 1, so minus 2, 79, constant decreasing. So that's 79.464. Then minus 79.464 minus this concentrated load, 376 over 7, express the answer in decimal, 25.75. So 25.75. Then minus 2 times 6, so minus 12. So it will be 13.75, constant decreasing. 13.75 minus 73.5, direct abrupt change. So negative 59.75. Then minus 2 times 2, minus 4, so negative 55.75. Sorry, negative 59.75 minus 2 times 2 minus 4, so negative 63.75 plus reaction at B, plus the reaction at B, it becomes positive 71.5. Then minus 2 times 2 minus 4 is 67.5. Then finally minus 67.5, so that closes the shear diagram. Then for the moment diagram, so we need to compute the areas of trapezoids. So area 1 is negative, area 2 positive, area 3 positive, area 4 negative, area 5 positive. Negative of area 1 is 0.5 of 83.286 plus 88.286 times 2.5. So area 1 is negative 214.364 kilonewton meter. So let's now have the moment curve from left to point A. So 0, negative increasing. So negative increasing curve here, negative 214.364. Then plus area 2. Area 2 is 0.5 of quantity 81.464 plus 79.464 times 1. So area 2 is 80.464. So negative 214.464 plus 80.464, you have positive decreasing. So you'll have here the ordinate equal to negative 134. Negative 134 plus area 3. Area 3 is 0.5 of quantity 25.75 plus 13.75 times 6. Area 3 is equal to 118.5 kilonewton meter. So negative 134 plus 118.5 is negative 15.5. Then plus area 4, which is negative, and area 4 is negative negative area 4 is 0.5 of quantity 59.75 plus 63.75 times 2. Area 4 is negative 123.5 kilonewton meter. So negative 15.5 plus negative 123.5. So we have negative increasing ordinate, so negative increasing slope. So it looks like that. So it becomes negative 139. Negative 15.5 plus negative 123.5 is negative 139. Finally, area 5 is positive. It should be 139 to close. So area 5 is 0.5 of quantity 75.5 plus 67.5 times 2. So area 5 is 139.0 kilonewton meter. And it is positive decreasing, so positive decreasing curve like that. So we notice, so that makes it 0. We notice that there's no positive moment in the entire section of the girder. Therefore, the elastic curve will all be concave downward. So concave downward everything, and it passes through the supports because there's no deflection at the support. So it looks like that. That's the elastic curve. So this is the complete construction of the shear and moment diagrams for this girder here and the sketching of its elastic curve. For our last problem about sketching of shear and moment diagrams as well as the elastic curve of a frame. For the frame loaded as shown below, construct the shear and moment diagrams. Also sketch the elastic curve. So this is the frame, and let's compute first for the reactions. So RD, we have AX and AY on the support A. So I assume that AY is downward and AX is leftward. So common sense leftward because there's only one horizontal load is rightward. So AX should be leftward. And because 26 is greater than 12.5, that's why AY is, I assume, downward. Summation moment about A equals 0, counterclockwise positive. So RD times 17, then minus or equals 26 times 12, 8.5 plus 3.5 is 12. The moment arm is half of 12, so 6. Then plus 12.5 times 12. Moment arm is 6 plus 5, 11. So R sub D is 207.176 kilonewtons upward. Then, summation moment about D equals 0, clockwise positive. So negative AY times 17, so 26 times 12 times 6 is clockwise, then equals counterclockwise moment AY times 17 plus 12.5 times 12 times 6. So AY is positive, so it's correct, downward, 57.176 kilonewtons. Then summation forces X equals 0, so 26 times 12 equals AX. So AX is 312 kilonewtons leftward. So next we transmit this load on this inclined member AB, but before that the load is 26 times 12. Then divide that by the length of AB, which is square root of 5 square plus 12 square. So the slope is 12 vertical, 5 horizontal, 25 hypotenuse. So 26 times 12, 312 divided by 13, the hypotenuse is 13. So that would now be the load. 26, 312 divided by 13 is 24 kilonewton per meter. So in construction, the shear moment diagrams for frames, the loading should be perpendicular and parallel to the member. So let's transform it into perpendicular and or normal and tangential component of load. So the slope again is 12 vertical, 5 horizontal, 13 hypotenuse. So the angle theta 1 is here, which is the angle between the vertical and the normal, or this angle here, this bigger angle. So that's theta 1. Then we have Wn1 and W tangential 1. Wn1 is equal to 24 times sine theta 1, which is 12 over 13. Again, W1 is hypotenuse is 24 kilonewton per meter. Then it is opposite of theta 1, so sine of theta 1, 12 over 13. So Wn1 is 24 times 12 over 13 equals 22.154 kilonewton per meter. Then Wt1 is 24 times cosine of theta 1, which is 5 over 13. Wt1 is 24 times 5 over 13 is equal to 9.231 kilonewton per meter. Then this is now the normal load, which is Wn1, 22.154 kilonewton per meter. Then the tangential up, which is 9.231 kilonewton per meter, or the normal load. Then this is the reaction at AX, and AY. Then let's resolve AX and AY into shear component or normal component or tangential component. So we will call the normal component as shear A because this is opposite the shear perpendicular to the member. The components of 312 is 312 times sine of theta 1. So this is longer. Component of 312 along this axis is longer. So 312 times 12 over 13. Then because 57.176 is downward, its component would be normal, and tangential is opposite to this direction. So it is going to the right, the tangential component. So 312 times 12 over 13 minus 57.176 times 5 over 13. This is the component of 57.176. So 312 times sine of theta 1 minus 57.176 times cosine of theta 1. So 312 times 12 over 13 minus 57.176, because this blue component along this axis here is going down to the right. So that's why it is 57.176 minus 57.176 times cosine of theta 1, 5 over 13. So V sub A is 266.01 kilonewtons. Then NA is the component of 312 is going down, same as NA. And the component of 57.176 is also going down, same as NA. So therefore, NA is equal to 312 times 5 over 13 plus 57.176 times 12 over 13. So it is cosine for the 57.176. So NA is equal to 172.778 kilonewton meter. Then we have at B, NB, then shear at B, let's say in that direction, and moment at B, let's say counterclockwise, because we anticipated the value. Then for the other segment, BC, 12.5 times 12, that's the total downward load. Now it's transmitted to BC, which is inclined, and the length of BC is square root of 12 square plus 3.5 square. It is 12.5. So therefore, the vertical load here along the member BC is 12.5 times 12 divided by 12.5. So it is 12 kilonewton per meter. Then this 12 kilonewton per meter is resolved into components, one perpendicular to BC and the other tangential to BC, like that. So this is the angle, theta 2. So W normal 2 is equal to 12 times cosine of theta 2. Cosine of theta 2 is 12 over 12.5, or we can transform it into the slope is 7 vertical, 24 horizontal, 25 hypotenuse. So going back here, NB is equal to NA, NB plus 9.231 times 13, NB. This is minus, so originally it's plus because it is in the left side going up. So NB plus 9.231 times 13 equals NA. Or in short, NB is equal to NA minus 9.231 times 13. So NB is equal to 52.775 kilonewtons. shear at B is equal to shear A plus shear B equals 22.154 times 13 because this is 13 meters long. So shear B is equal to shear at A minus 22.154 times 13. Likewise, moment at B is either V sub A, we look at here, V sub A times 13 minus 22.154 times 6.5, the moment arm of 22.154, because this is 13, half of 13 is 6.5. So 22.154 times 13 times 6.5. Or in short, MB plus MB counterclockwise plus 22 point plus, this is originally plus in the left side, plus 22.154 times 13 times 6.5 equals V sub A clockwise moment, V sub A times 13. This is V sub A times 13. Or MB is V sub A times 13 minus 22.154 times 13 times 6.5. So MB is equal to 1586.117 kilonewton meter. Another way of computing MB is equal to AX 312 times 12 minus AY 57.176 times 5 minus 26 times 12 times 6. Or MB is 312 times 12 minus 57.176 AY times 5 minus 26 times 12 times 6. So it will give us the same value of 1586.12 kilonewton meter if we round off that to 1586.12 kilonewton meter. So going back to this segment BC here, this is theta 2. So theta 2 is, slope of theta 2 would be 7 times 2, 3.5 times 2, horizontal times 2, so 24, and the hypotenuse is 25. So that's why WN2 is 12 times cosine theta 2, 24 over 25, is equal to 11.52 kilonewton per meter. While W tangential 2 is 12 times sine of theta 2, 7 over 25. So 12 times 7 over 25 is equal to 3.36 kilonewton per meter. So let's now transmit the normal and tangential load. Normal is 11.52 kilonewton per meter. Tangential is 3.36 downward kilonewton per meter. So next, we have to compute shear at B from this diagram here. Shear at A plus shear at B equals 22.154 times 13. Or shear at B is V sub A. Or shear at B is 24.154 times 13 minus V sub A, 266.01. So shear at B is equal to 21.992 kilonewtons. So this is the reaction at B, 207.176. There's only one reaction at B, so it's easy for us to resolve this into shear or normal component and tangential component. So this is shear at C, which is 207.176 cosine of theta 2, and cosine of theta 2 is 24 over 25. This is normal at C to B, so this is 207.176 times sine of theta 2 times 7 over 25. Call that NBC, shear BC. Then let's draw the element extension here from B to the next member. This is BC, so we have this corner here. Then let's transmit the shear, 21.992 shear at B. Then normal is 52.775. We already computed that in the preceding slide. The moment is clockwise, which is forgot 0.12, something 0.12. Then counterclockwise again here. Then shear is up to the right, and normal is up to the left because it should be pointing opposite to this. So this is the adjacent free body diagram for BC. We already computed V sub C and N sub CB. And let's verify V sub BC and NBC if it is in equilibrium. So summation forces X, use this diagram here. So V sub BC times sine of theta 2, which is 7 over 25, then minus NBC times cosine theta 2, which is 24 over 25. So VBC 7 over 25 minus NBC 24 over 25, then plus 21.992 times cosine of theta 1, which is 12 over 13, then minus 52.775 because this is going to the left. Sine of theta 2 is 5 over 13 equals 0. Simplifying, 7 V sub C minus 24 NBC equals 0. Call that equation 1. Then, summation forces Y equals 0. So V sub BC times cosine of theta 2, which is 24 over 25, plus NBC times sine of theta 2, which is 7 over 25. So VBC 24 over 25 plus NBC 7 over 25, then equals 21.992 times cosine of theta 1, which is 5 over 13, plus 52.775 times sine of theta 2, which is theta 1 rather, which is 12 over 13. Simplifying, 24 V sub BC plus 7 NBC equals 1429.346. That's equation 2. So these equations are merely trigonometry and statics. So if you still find this difficult to absorb, it means your trigo is not enough, or maybe you have to review your trigonometry. So you're already, I expect that you are already a student in structural analysis. So I hope this computation of components are not difficult for you to absorb. Because if it is still difficult, it's because you're not yet prepared to be in structural analysis subject. So you have to review your trigo and your statics. So in short, if you find this difficult, even if it is elementary trigonometry and statics, you're still not prepared to be in this course structural analysis. So for those who are able to absorb this, then you are ready to take higher civil engineering subjects for that case. For those who find it difficulty, so I suggest that you have to review your trigonometry and your statics. So solving these two equations simultaneously, we have shear BC 54.887 and NBC equals 16.009 kilonewtons. So shear at C is 207.176 times cosine of theta 2, which is 24 over 25, 198.889, and NCB 207.176 times sine theta 2, which is 7 over 25. So it is equal to 58.009 kilonewtons. Then let's check NBC 16.009 plus 3.36 times the length of this is 12.5, then minus NCB, which is 58.009. That's approximately 0, so that checks equilibrium of this member also. Then summation forces tangential, so we have V sub C, which is V sub C is equal to what is V sub C? 198.889, then minus V sub BC, which is 58.887, minus 11.52 times 12.5, and it is almost 0 also. That checks. Remember that shear moment at C is 0, so summation moment about C is 0. Moment at C is 0 because if you can remember, reaction at D is vertical and the member CD is vertical. So if you sum up moment anywhere on section CD from C to D, the moment is 0. So that's why we should equate moment here to 0. So considering clockwise positive, we have MB, which is 1586.117, then minus V sub BC, which is 58.887 times 12.5, minus 11.52 times 12.5 times moment arm 6.25, that's almost 0 also. So that checks equilibrium of member BC. Now that we have checked equilibrium of BC, we are now ready to draw the shear diagram and the moment diagram. For the shear diagram, the shear at A was, it was from 0 to the shear at A, which was 266.01. Then minus the loading here, which is rectangular, the loading is, what was the loading? 24 times 12 over 13. So the loading is, the uniform loading was 22.154. So 266.01 minus 22.154 times 13, the length is 13. So 266.01 minus 24 times 12 over 13 times 13 over 13. So we get 21.992, negative 21.992. So the point where shear is 0 can be obtained by dividing 266.01 by the uniform loading, which is 22.154. So 266.01 divided by 22.154 is the length here, 12.007, or 12.007 can be computed by similar triangles. 266.01 as to x1 equals 21.992 as to 13 minus x1, you get 12.007. So therefore this distance is 0.993. 13 minus 12.001 is 12.993. Remember that the shear in BC is going down 887, then plus minus 11.52 times 12.5, negative 54.887 minus 11.52 times 12.5, this one minus 11.52 times 12.5, straight line increasing. So we have negative 168.88, 198.887 minus 11.52 times 12.5. So negative 198.887, then plus V sub C, which is 198.889, so that is approximately 0. There's a small discrepancy. Then here, there's no shear and moment in this section, so that's just the complete shear diagram. Another way to solve for 12.001, we establish the shear equation here. It is 266.01 minus 22.154 times x1 equals 0. We equate the shear to 0, so you get 12.001. For the moment diagram, 0 moment at A, then you compute this area. That area is equal to 1/2 of 12.007 times 266.01. Then the small area there, which is negative, call that area 2. Then the area of trapezoid, area 3. So area 1 is 1/2 or 0.5 of 12.007 times 266.01 is 1596.991 kilonewton. And it is positive, decreasing till 0 slope or parallel to this inclined member slope. Area 2 is negative 1/2 of 0.993. This is 0.993. 13 minus 12.007 is 0.993 times 21.992, so negative 10.919. Area 3 is negative, area 3 is 1/2 or 54.887 plus 198.87 times 12.5. So area 3 is negative 1586.088, which is expected 1586.117. But there's a small discrepancy because we round off values. So that's okay, that's acceptable. So from 0, we have positive decreasing slope. So maximum moment is area 1, 1596.991. Then plus area 2, which is negative 10.919. So 1596.99 minus 10.919 is 1586.071, which is supposedly the moment at B, 1586.12. But again, we tolerate a very small discrepancy. That's the reason. So moment at B, we should begin at 1586.117, then plus area 3, which is negative 1586.08. So that makes it almost zero here. This is negative increasing. So it should look like that. Negative increasing should look like that. Negative increasing curve. So like that. And that's almost zero there. Then the rest would be zero for CD because the moment in CD is zero everywhere. And for the elastic curve, we have positive moment here, positive moment. So it looks like that, concave up with respect to this inclined member. So it's like that, concave up, then slant, because there's no moment here. So concave up, then we just make this portion slanted straight like that. Now, why is this concave up? Because we have positive moment. Why is the corner here below? Because the effect of the load is to push the member to the right, so it translates to the right a little, and we have vertical load here, so it drops a little also. And because of this loading here, which is downward, it will make the curve or elastic curve like that. Then this portion here, because this roller here will be moved to the right also, it will move to the right like that. So that's the explanation why the elastic curve looks like that. So I hope that you follow the solution, and if you cannot, you have to review, as I said, trigo and statics, because the manner these loads are transformed into normal and tangential components is by means of statics and trigonometry. So if you find it a problem, your problem is not structural analysis, your problem is statics and trigonometry. So you have to review them, because once you are a student in structural analysis, it is already presumed by the instructor that you are completely good in trigonometry and in statics. Because if you find this difficult, it means that your background in trigonometry and in statics is not that high, not good in this level, because you still find it difficult. So I suggest that you have to review all of them, so that once you master them, then it's easy to follow the solution here. So that's all, and see you in my future videos. Bye-bye.